All right, so now we're ready for chapter three. And so chapter three has some very important concepts in here. Some of these are very abstract, but they're very important results. And some of these are meant to be something that we'll be using throughout the rest of the course. In particular, this discussion about maxima and minima, um, applied optimization, that's all awfully important as well. But and some of these others, L'Hopital's rule is a method for dealing with limits that we have not encountered before. And Newton's method is a method of optimization as well. But all of these are very useful techniques, but I would say that the most important one is maxima and minima. We will spend quite a bit of time studying those concepts throughout the course, and of course, well into calculus 2 and 3 as well. So now, some of these, like I was starting to say, some of these results are somewhat abstract, but we'll go through them carefully and make sure that we understand them. And then some of these are meant to be more practical and down to earth. So there's a little bit of everything in this chapter. Anyway, so when we start at the beginning, we have first we start with this notion of linear approximations. Now, what is this all about? Well, in the real world, we often find ourselves using linear functions to explain the behavior of different variables, even though in many of those cases, whatever it is that we're trying to study is not strictly speaking linear. It may be close enough that we can use linear functions to at least approximate its behavior. So, and that's a good thing too, because linear functions are very simple. They're very easy to deal with. So whenever possible, we'd like to use linear functions, even if we're trying to use them to model something that is not, strictly speaking, linear. So what we're going to discover here is that no matter how a function behaves, there may be intervals, short intervals, over which its behavior is at least approximately linear. Let me just throw a couple of sketches up here so you can see what I mean. So imagine here's some function or other. Now, this is a very interesting function. It looks like it's a cubic function, but right about here, let's say we call this point A. You can see that at least right around this area, within, let's say, this interval, the function does appear to be very close to being linear, at least within that interval. Now, it's important to note that outside this interval, the function's behavior is not linear at all. But at least within this narrow range of values, it looks like we can use a linear function to at least approximate what's happening here. And so we'll often find that when we're trying to use a linear approximation, it really only applies within a small area. And so, like here, for example, this could be thought of as a plus delta x, or dx rather, and a minus dx, with the understanding that dx is an extremely small value. So then within that interval, at least, we can make the case that a linear function could do a very good job approximating f of x. So anyway, now what we're going to do is start with this equation. In a situation like this, it's important for us to be able to calculate the equation of this tangent line. Okay, notice how I've drawn a tangent line to the curve at that point. And the point of that is that the tangent line touches the curve at exactly that one point. So if we're going to approximate the value of this function in this interval, we're going to use it with this tangent line. Okay, so that means what we need to do is have a formula or create a formula for the tangent line at this point. Now, this is the formula. And what we're going to do now is take a step back and see why this is, in fact, the correct equation for a tangent line at this point. By the way, one more thing that I should have labeled here is that if this is A, this is f of A. We're going to need both of those in our equation for the tangent line, as you can see. Anyway, so here's what we're going to do. All right, well, here's another example. We have a function which is clearly a curve, and this straight line could be used to approximate the value of this function in the area close to A. Okay, so here's A, here's f of A. Now you can see as we get further and further away from A in both directions, the approximation worsens as we get further and further away from A. But when we're really close to A, we can have a very good approximation um, as long as we don't get too far away. All right. So now, by the way, if we are going to need to move to another part of this curve, we probably would need a different tangent line. So, but because we're, for whatever reason, we're interested in understanding the value of this function in the area around A, we're going to use this linear approximation to come up with values for, let's say we need A plus D of dx. We can use this tangent line to come up with at least an approximation to find an approximate value for f of A plus dx. Okay. Now, I'm just going to quickly show you, I chose this function for a reason. If you have had any background in finance or economics, you may recognize this curve. This actually shows us the relationship between the price of a bond and the yield of a bond. It's often called the price yield curve. And so what will often happen is it's known that when yields rise, bond prices fall and vice versa. The problem is this curve that we're seeing here doesn't have an explicit formula. There's no equation that tells us all the values along this curve. We only observe them in the market. In other words, we have observations on different yields and prices. So if you're, let's say right here today, you have a bond whose price is here and whose yield is here. And you're pretty sure that tomorrow the Fed is going to raise rates so that the yield goes up to, let's say here, I'll call it Y star plus DY. I want to know what's going to happen to my bond price. And using this technique we're about to use, that would put me right about here. We could call it P of Y star plus DY. With the understanding that it's not precisely correct, but as long as that change in yields isn't too large, then our approximation should be quite close. Anyway, so let's get back to this and see why this equation works. Okay, why is this the correct equation of our tangent line? All right, now the first thing we have to do is a quick review. I'm going to sneak this onto here. If you recall, everybody remembers the equation of a straight line. Okay, but it turns out you may have forgotten that there's another way of writing the equation of a straight line. This is the slope-intercept form. Because it contains clearly the slope m and the intercept b. But there's another way of writing the equation of a straight line, and it's called the point slope form because it contains the slope. And we're assuming that this point x0, y0 is a point on that line. So this equation will also give us the equation of that straight line in a slightly different way. And so for some purposes, like the one we're about to use, it's more convenient than the traditional slope-intercept form. So let's revisit this diagram. And just a quick reminder of the point slope form. Nope, we don't want that. Here we go. Okay, so we're starting at point A, okay? We're assuming that we know the value of this function at A. So we have f of A. F of A is known to us. And then we're going to describe this tangent line, and we're claiming that what you're seeing down here is the correct equation for that tangent line. Okay, but where did this come from? Well, again, given the way this diagram is drawn, I'll tell you what, let's see if I can, just so you can see what you're doing. Let me just quickly sketch it in here again. Okay, so this is the point A comma f of A. So we know that, well, what we don't know is the slope. Okay, we do know the one point that's on this line, this tangent line, I mean, and that's the point A f of A. So you can think of this as what we're earlier calling y0 and x0. So this y0 becomes f of A, and x0 becomes A. Now, here's the interesting part. The slope of this tangent line, remember, the tangent line, the slope of the tangent line at that point equals the value of the first derivative evaluated at that point. Okay, so that's why here we're going to write f prime of A. Okay, so in other words, remember the slope of the tangent line at that point is the derivative of that function evaluated at A. So that's where this thing comes from. And then, we have to do a little algebra on it, but this is the final result right here. This is the equation of the tangent line. At point A. Or what we could do is say where x equals A. And that's it. That's our equation. Now that we have this, we can now go ahead and use it to come up with some approximations. All right, like this one. Here we've got f of x is 1 over x, the inverse function. Recall that looks like this. Now, this is clearly a nonlinear function. And in fact, it's pretty far away from linear. But if we're only interested in the value of this function near a specific x, and here's a Symbolab's version, well, then we may be able to use these techniques to determine the value of the function when really close to that point. Here, that point is 2. So, of course, if you recall from the power rule, if the original function was 1 over x, by the way, let's not forget that this is the same thing as x to the minus 1. And now that means that for the power rule, that implies that k is 1 and is 1, a negative 1. So when you take the derivative, you'll have minus 1, 1, x to the minus 1, minus 1, which leads us to minus x to the minus 2, which is the same thing as minus 1 over x squared. Okay. Now, we're interested in studying the value of this function close to x equals 2. So I've actually, here it is. I put this graph in here so you can see it better. This is where we're interested in x. This is A, and this is f of A. So what is the equation of that tangent line? Okay, well, what do we know so far? We know that A is 2. F of, actually, what we forgot to do, we forgot to notice that f of A is simply 1/2. F prime of x is, of course, 1 over negative 1 over x squared, as we just saw. negative 1 over x squared. So f prime of 2 is negative a quarter. So we have a, we have f of a, prime of a. And so when we plug these into our equation, guess what we get? Okay, so again, this is f of a. This is f prime of a. And this is x minus a. And then when you do a little algebra, this is your final result, 1 minus 1/4 of x. And you can see, well, that looks good because now, of course, I've only sketched it in here, but you can see that this is consistent with the vertical axis being, the vertical intercept being 0, 1, and the horizontal intercept being 4, 0. And you can see then the intercept is 1, and the slope is negative a quarter. In other words, this equation right here is written in the traditional b plus mx form. All right, so that means we've done this correctly. You can see that it works. Now what do we do? Well, all right, suppose for whatever reason, I need to come up with an approximate value of f of 2.1. Let's see. So here's your 2. And the tangent line is, as we just saw, 1 minus 1/4 x. Here's 2. What about 2.1? All right, well, my drawing is a little small to see. Let's see if we can put it on here. Or even better, let's do this. So we're looking for, let's try this again. Okay. Well, that helps. Since we know the value of the function when x equals 2, if x is 2.1, and you see what I'm trying to illustrate here is that that point is not on the green line. That's the actual function. It's on the tangent line. So this is what we mean by f of 2.1. Sorry, this is our approximate value. I shouldn't write it like that. This is the approximation to 2.1. I'll tell you, let me write it like this. Whatever that number is, it's approximately what you would get from f of 2.1. Now, how do we find that number? All right, well, here's the equation of the tangent line. And so we're going to plug in this number. And so in other words, you're replacing the x with 2.1. So actually, this should have said approximate right here to indicate, remember, these symbols mean approximately equal to. To distinguish it from these, which are clearly equals. So we're getting 0.475 there. Okay, so because in this case we do know the actual function, if you plug that in, you'll see that it's about 0.47619. So the approximation turned out to be 0.475. The actual is about 0.47619. So we've our approximation is a little too low. And you can tell by looking at this graph that that's what was going to happen, because if you see here, the tangent line is everywhere below the curve. So that means that the approximation, in this case at least, is going to be somewhat smaller than the correct value of f of 2.1. If we were doing this down here in this part of the curve, it would have been the other way around. Okay, so you can see that the approximation is not that terrible. And of course, but we don't know what this application is. We don't know how close we really need to be, but at least we know that we're not really that far off. I mean, 0.00119 is a pretty small percentage of the actual value of 0.47619. So it appears that this is a pretty good approximation. But if I tried this for 3, you can see I'd be way out here somewhere. And you can see the spread between the curve and the tangent line is getting bigger. And so the approximation would be worse. And if, oh my God, I tried something out here like 10, the approximation would be pretty terrible. Really terrible. So this only works when we're really close to A. Yeah, you can see 3. I didn't remember having done this. 3, the actual value, I'm sorry, the value that we're getting on the tangent line is 0.25, but the real value is 0.333. So, the error went from 0.00119 to 0.08333. That's a huge increase, like 80 to 1. So it makes a big difference how close you are to the original A. Okay. So now sometimes this what we're seeing here is called the linearization of f of x near A. It has other names too, but what I'd like to point out here though is that up here you see what we've done is we've written this as an approximation because this is the tangent line. So this L will be written like this. It's an equality. It's the same function. And now we're going to use it to come up with some more approximations. Okay, so here's the square root, and you can see in this case, the tangent line tells me what you're seeing here is that we're going to attempt to do is approximate f of 9.1 from the tangent line. Okay, so we already know that f of x is 3. So we're going to try the square root of 9.1. And let's see how close the approximation is. Now, based on that curve, you can see that whatever number we get will be a little too high because the tangent line is above the curve. So let's see how high it is. So, of course, we need to know f prime of x, and here's our old friend, the power rule. Remember, the square root is just another name for x to the 1/2 power. Is 1, x is, n rather, is 1/2. So based on the power rule, that's going to be a half times 1 times x to the 1/2 minus 1. This can be rewritten as 1 over 2 radical x. And so let's tell it. Let's go grab that function again. Just so it's all together in one place. So once again, we know that the function is the square root of x. A is 3, 9 rather. F of A is therefore radical 9, which is 3. F prime of x is 1 over 2 radical x. Okay. And f prime of a is f prime of 9 1 over 6. Okay, so we pretty much have everything we need. We bring these together, and here's our final result. And of course, this one, you could leave it like that if you wanted to, but we usually just rewrite it in the traditional slope-intercept form. And so that would be here. That's what we mean by our linear approximation, by the way. So now to solve for f of 9.1, we're going to solve this linear function at 9.1. And when we do that, you'll see that it's about 3.01667. Now, f of 9.1, the actual value that we should have gotten, square root of 9.1, hold on. I don't happen to have that one memorized. Is about 3.01662. That's pretty close. Yeah, that's pretty impressive. Yeah. So yes, but again, because we were so close to the original A, this is what you would expect. Okay. So like I said, that one we'll come back to this again. That was one of the more abstract ideas that we'll be looking at. Now, differentials. We've briefly discussed this. We mentioned that Leibniz, who is pretty much given credit along with Newton for inventing calculus, they both worked independently of each other. Leibniz lived in Germany. Of course, Newton lived in England, and they wrote about the same time. Newton in particular was very secretive about his results. He didn't want to publish anything until he was 100% sure they were right. So he probably invented calculus quite a bit earlier than his first published papers would suggest. And so there's always going to be controversy about who got there first, but um, they certainly didn't know each other. I don't think they'd ever even heard of each other. But especially in those days, remember, this is the early 1700s, late 1600s. People live in Germany and England are not necessarily going to bump into each other. We didn't have the internet or anything like that, so they could have never heard of each other. But anyway, Leibniz came up with this differential notation. And so f prime of x, he wrote it as dy dx, where the d represents a differential, which is an extremely small, or think of it as an infinitesimally small change in x or y. And as opposed to delta, which is a small change, but not infinitesimal necessarily. And in fact, you could think of the limit of delta y as delta y goes to 0 as dy. As it's getting really, really close to 0. We call it dy as opposed to delta y. But sometimes, now you notice that what's interesting about this notation is that we can actually rearrange it algebraically and rewrite this as dy equals f prime of x times dx. And sometimes that's very helpful. And so basically what it's trying to capture is if there's a small change in x, what is the impact on y? So how does this tie in with these approximations we were just looking at? Well, here's what we're going to do. We're going to assume that the difference between x and a is really, really small. Okay. So in other words, when we're drawing all those diagrams, this is a. There's the tangent line, and then this would be our a. We're going to call this a plus dx. And the approximation we come up with from the tangent line is called f of a plus delta x. Just to reinforce the idea that we're only doing this approximation within a very close range of the original a. So anyway, what this does is it's showing us that if you go through all the algebra, you'll see that, let's see if we can draw a picture of this. It's telling us that this difference is approximately equal to the slope of that tangent line evaluated at a times dx. So look at this, is this distance here is dx. So when there's a dx increase in a, the function increases by approximately this. Now this diagram, after drawing on it, it's gotten a little cluttered, but you can see that the blue curve is the actual function. The orange line is our linear approximation. And so you can see that in this case, our linear approximation is a little too low. And the difference between these two, you can subtract this one from this one, and you can see that what we're able to do is figure out how much the function will increase approximately as when a goes from a to a plus delta x. And so here, this is the error. How far off are we going to be? Okay. So in other words, all they're doing is showing you how what we were just doing ties in with differentials. So here we go. Here's another one. We have y equals x squared plus 2x. Now we're going to solve for these differentials. And so we start, here's our function. This is approximately, actually, I'll tell you what we should probably do. Let's go look at Symbol Lab for a minute, just in case my sketch isn't what it could be. It's x squared plus 2x. Oh, well, it wasn't so bad. Oh, I see why I drew it myself, because you can see we need, yeah, 3, when x is 3, right about here, y is 15, which is way up here somewhere. So this sketch isn't too terrible. All right. I don't know, maybe I can improve on it a little bit. It's a very steep parabola rather. So if dx equals 1.1, that means what we're going to do is try to figure out the value of this function when x is 3.1. If the change, dx is the change. So what we need to do is find the value of this function when x equals 3.1. using our linear approximation. So let's see, let's go through this step by step. Yeah, I know it's all cluttered onto here, but let's go through this step by step. We of course start by calculating the derivative of x. And of course, using the power rule, the derivative of x squared plus 2x is 2x plus 2. And the value of a is 3. Okay. And therefore, because dx is 0.1, what we want, let's see, that's good. But here, what we're going to do is maybe approach this slightly differently with these differentials. Remember that f prime of x can be written as dy dx. So therefore, dy is 2x plus 2 times dx. And remember, the dx is the change from a to a plus dx. So if we chose x to be 3 and dx to be 0.1, that means the approximate change of y is 0.8. Okay, so there's here, we're not thinking about, we didn't directly calculate the new value of y. We figured out the change. So what this is implying is that since f of 3 is 15, and when dx is 0.1, dy is 0.8, which implies that f of um, 15.8. Okay, so what we're saying here is that what we've calculated is the change or impact on y rather than the new value of y. But that's easy to figure out. Once we know the change of y, then we just add it to the original y, and we end up with an approximation of 15.8. Now, if you look at this graph, you'll see that our approximation is going to be a little too low. Okay, because the tangent line is below this curve. So we can also determine that since the function is 2 x squared plus 2x, if we want to know the exact value of f of 3.1, well, here it is right here. It turns out to be 15.81. So our approximation is only off by about 0.01. Okay. So the change, the estimated change is 0.8. The actual is 0.81. So it was awfully close. Okay. All right. So now we can move on to, like I said before, I think this is almost certainly the most important topic in this chapter. I think there's no doubt. I mean, it all ties together here, but this is really what we're aiming for. This concept of maximum and minimum. We're going to see this all the time throughout this course and any other calculus courses you ever take. And the idea here is that a function can have several points where it reaches a maximum or minimum value. But there's different ways, there's different types of maxima and minimum. Now, by the way, just to avoid confusion, just be aware that the word maximum, when it's pluralized, call it maxima. And when we take the word minimum, when we pluralize it, it becomes minima. That's because these are Latin words. Okay. So maximum becomes, oh, what did I do? Sorry. Well, I really goofed this one up. Plural, the plural is minima. Also, I want to point out that um, there's a word called extremum, which includes maximum and minimum. In other words, a maximum and a minimum are both an example of an extremum. And when you pluralize extremum, it becomes extrema. So maximum becomes maxima, minimum becomes minima. Extremum could be either or, okay? And the plural is extrema. All right. So here's a little sketch that I did. And you can see this is some kind of polynomial. And you can see that it goes through these ups and downs like a roller coaster. And so at x1, we reach a point which is called a local maximum. Now, why is it called that? If you look carefully at this function, you can see that there's another point where it reaches what appears to be a maximum, but that maximum is only in the neighborhood of x3. Over here, it's within x1. So in other words, it's like within this area, that's the highest that the function will reach. There can be more than one of these. And so you can see from the graph, there's two, what we call local maxima. And also another point of notation here, or terminology, I should say, the word local and relative in this context mean the same thing. Local, relative. Either one of them describes the same situation. Local, I guess, because it's, you're like only in that area, that's the largest point. We also, of course, can have a local minimum. Interestingly enough, though, um, if you notice, this function does get smaller than this point. Down here, the function is going down to negative infinity. Same thing over here. So that minimum only applies within that area. It's not the smallest value of the entire function, but it is within that immediate area. Okay, so we can call these local extrema. And so here it's more straightforward. We also can call them relative extrema. And so they're not necessarily, and by the way, if you notice, now this one, we have the function here comes from negative infinity. This one is going up to positive infinity. So that means that this local maximum is not the largest value in the entire function. You can see over here on this side, there are plenty of values over here that are larger than this local maximum. Down here, this local minimum, it's the same thing. So again, the idea is that local or relative only applies in that intermediate area. Sometimes it's called an interval, sometimes it's even called a neighborhood. So is there a point okay. Well, hold on. Let's just formally define these. The formal definition of a local maximum is f of x has a local maximum at x equals the point C, providing there's an open interval. Now, by the way, here the word open means not including the two endpoints. Okay, so we went over this in the review section. When you have intervals like this, remember the round parentheses means it does not include the A or the B. Then the other extreme is the closed interval. includes both A and B. And then the other ones, remember this one includes B, but not A. And this one includes A, but not B. This could be called, it depends on what book you're looking at, semi-closed or semi-open. This is like looking at a glass and saying, is it half full or half empty? It's, it could go either way. But anyway, so the words open interval implies that you're not including either endpoint. But for everything inside that interval, if we find a C such that the function has a larger value nowhere in that interval, then that point C is where we find our local maximum. Okay, so in other words, within this interval from A to B, the function never gets any larger than f of C. That makes this a local maximum. And of course, the reverse for local minimum. Okay, there's no place in that interval where the function gets any smaller. Now, of course, we're going to need to figure out where these are, if there are any, if they exist. So, oh, one more thing. I do want to mention this before we go any further. We've been talking about local or relative extrema. What else is there? Let me just throw this in here. The largest point where a function reaches its maximum value within the interval AB is a local or relative maximum. The point where the function reaches its minimum value within the interval is a local or relative minimum. But there's others. There's two other possibilities. Here we go. Actually, I'm going to copy this so I can just change the keywords since we're running out of time here. The point where a function reaches its maximum value within the entire domain of a function. In other words, that's it. There's no place else in the entire function where the function gets any larger, is we're going to call either a global or absolute maximum. Aha. And then, same thing for the minimum, within the entire domain of the function is a global or absolute minimum. And we'll get to those two. So I'll show you a couple of graphs here, just so you can see the difference. So this one you've already seen. But over here, what if you have a parabola like this? Function doesn't go above that point. You have this parabola. And by the way, there's a reason why I'm drawing those tangent lines there. We'll get to that in a bit. This is a global or absolute minimum. So now a function can have a mixture of both. I mean, there could be, in fact, there can be a large number of different local extrema. There can only be one global, though, and there may not be any. Um, for example, if you have something like this, there are no extrema here. Okay, it just goes on and on forever, up to positive infinity and negative infinity. Okay, so anyway, so we have our local maximum, we have our local minimum. Now, this is a very important idea. The point at which these occur is called a critical point. Okay, so a critical point occurs when either the derivative at that point is zero, meaning that a tangent line to the function at that point is horizontal. But it turns out we can also have a critical point where the function, the derivative rather, is undefined. Now, that can happen for at least a couple of different reasons. There might be a discontinuity there, but also if there's a sharp break in the function, like something like this, then here, I probably I shouldn't draw that line there because that looks like it's our tangent line. Let's leave that out. At this point, f prime of c is undefined. The whole idea of a derivative is that you're approaching a point where the changes from either side are getting smaller and smaller and getting close to that value. And so we'll go over this more later on, but if we have a sharp break in the curve like that, then the derivative is undefined. So a critical point will either occur at one of two places. Either the derivative is undefined, or else the tangent line is flat, meaning that the derivative has a value of zero at that point. So when we look for these maximum and minimum points, we're actually looking for the critical points that'll point them to us. In other words, this is how we find them. Okay. Wow. How do we do that? Well, this is why we had to save this discussion for chapter 3, because this means we need derivatives. Okay. So what we're going to do, by the way, I do want to mention this. If f of c is a local extremum, then c must be a critical point. But it turns out it doesn't have to work both ways. In other words, if c is a critical point, then f of c is not necessarily a local extremum. You're probably wondering, how is that possible? Well, it has to do with the ones that are undefined. So we'll discuss this in more detail in a bit. This is building us up to a very important result in calculus called Fermat's theorem. Fermat was a very famous mathematician. He was very famous. There was an incident. Fermat had a tendency, he had a very extensive library of math books. And when he was reading them, he had a tendency to take a pencil and write little notes to himself. And ideas would occur to him while he was reading these books, and he would write little notes to himself to come back and check this out later. So there's one book he was reading, and I don't remember the name of it, but he wrote in the book in his little pencil, whatever the result was, he wrote, "I have found a very clever proof," and he never wrote it down. He guess he forgot about her. He never got back to it. He died and he forgot whatever happened. And so it took hundreds of years for mathematicians to come up with the proof that he claims that he found and wrote down in his book. It was kind of an interesting mathematical puzzle. Um, I think if you go to Wikipedia, Fermat's last theorem, Fermat's conjecture, states that a to the n plus b to the n equals c to the n for any integer greater than 2, that no three positive integers can satisfy that equation. So in his book, oh, I didn't, okay, Arithmetica, an ancient Greek text in 1637, he wrote, okay, I found this wonderful proof, and he never wrote it down anywhere else. It took until 1994 for a British mathematician to find that proof. How do you like that? But he, he, yeah. Now we don't know if it's the exact same proof that Fermat had in mind, but we know that this one does work. So it was one of those puzzles in mathematics that, everyone wants to be the first one to get to this. So finally it was solved. But it took 358 years to get to that point. So that tells you, write everything down. Um, all right. Anyway, so what we're going to do is the next time we'll pick it up right here with Fermat's theorem. We have to understand how to identify critical points, and then we have to figure out if they're showing us a relative maximum, a relative minimum, or possibly neither. We have to understand how to distinguish between the three cases. So all that can wait till next time. Okay, so I'll see you then.